All right, gang, Math 6620 here. What we're going to do in this video, and I suspect that this is going to be a rather lengthy video, and I have no idea how long it's going to take, obviously, is I want to look at a complete example of a principal component analysis and factor analysis. In the previous video, what I did is I gave you some matrix techniques, and we're going to revisit those. But I wanted to go ahead and get on the books a complete example using R. It turns out that if we have a raw data, then we're going to run principal component analysis, factor analysis. It's best to use R. But sometimes we're just not given our data set, but we're just given the summary of our data with a correlation matrix. What you're going to need to do in this situation, and you'll probably have a homework assignment that'll require you to do this, is you'll use matrix operations. Now, you can use R, you can use Mathematica or whatever may work for you, but you clearly would need to use matrix operations if you're just given the correlation matrix. All right, gang, a lot of stuff going on here, and I'm sitting here trying to kind of get my mind wrapped around all this. Let's go ahead and talk a little bit about the data set that we're going to use here. The data set I have here is some placement information that I got my hands on, and what this was, or at least my understanding of this is something that was collected from I don't know, 73 high school students, and what they did is they gave a kind of a placement test, or at least an achievement test, if you will, of 6 subject areas in mathematics: calculus, trig, problem-solving, logic, statistics, and algebra. And what they did is they gave 50 questions in each. So they gave 50 questions in calculus, 50 in trig, and so on and so forth. This first student that I've got highlighted here got 9 questions out of 50 correct in calculus. They got 12 questions out of 50 correct in trig, 3 questions correct out of 50 in problem solving. Sounds like they need to work on their problem solving skills. And, you know, at the end, 21 questions out of 50 in algebra. Now, the purpose of principal component analysis and factor analysis here is kind of twofold. First of all, I'd like to examine this, so I'm going to go back to this. So our purpose is twofold. And I think I called this math skills .csv, and I think that's the way it's presented on Blackboard. So our goal is twofold. I want to use PCA and factor analysis to see if I can identify an underlying structure, you know, that's not just visible with the human eye. The second thing I'd like to do is I suspect that some of the variables are highly correlated. So if I wanted to use this data in multiple regression techniques, then I have a multicollinearity issue. Guys, remember when your predictors are highly correlated, let's say, for example, that we wanted to use calculus and trig and all these different scores to predict, for example, how someone would do on an ACT or whatever it may be, I would have a hard time using all these variables because they are probably so highly correlated, and I would get into a multicollinearity issue. So what I want to do is I want to examine to see if there are any components that pretty much does an adequate job of explaining the variation that these 6 variables explain. Okay, so I want to see if there's any underlying structure that can help me achieve 2 goals here. And I think this actually turns out to be kind of cool. Now, first thing we need to do is some preliminaries. And preliminaries that I have, do we have any low correlations? High correlations? Sample size issues? And do I have a normality issue? These are preliminaries that I'd want to take a look at before I begin a principal component analysis, okay? Now, the first one is low correlations. Typically, when I have a lot of correlations below 0.30, then that could be problematic, okay? Now, again, what is a lot? Well, a lot is clearly subjective, and I presented it that way on purpose. So, guys, what it looks like to me, I'm getting ready to crunch some data, so I need to bring R into play. Again, I'm pretty sure that I called this math skills. Cool. All right. So the variables, I like to have those easily accessible because, obviously, if the C is capitalized, it makes a difference. Now, first thing I want to do is take the correlation. So look, create the correlation matrix. And I don't know, people are different, obviously. That bothers me that all these correlations are presented to 7 places. I prefer 2 or 3. So I'm going to round the correlation matrix to 3 places and just clean it up a little bit. So guys, I got tunnel vision right now. Do I have too many small correlations? Well, when I look down calculus, I see that I've got 1 that's below 0.3. Just focusing on the ones below 0.3 right now. I've got 2 in trig below 0.3. I've got 1 under logic, 2, 3 under stats. So I've got issue to investigate this low correlation issue. So guys, here's the way we do that more objectively and more technically. What we run is we run a Bartletts test of correlation matrix. Now, guys, let's, let me back up a little bit. What the Bartletts test of correlation matrix does is it compares 2 matrices. It compares the identity matrix with our correlation matrix. Okay? Now, let's think about the identity matrix. Let's say, for example, that we are looking at the correlations between variable 1, variable 2, and variable 3. Now, obviously, in this situation, we have 6 variables, but let's just say, hypothetically, we're looking at 3 variables, okay? We know on the diagonals we're going to have 1 because every variable correlates perfectly with itself. But let's assume that V1 and V2 aren't correlated, V1 and V3 aren't correlated, and V2 and V3 aren't correlated. Well, if you think about it, if we have no correlation between V2 and V3, V1, V2, V3, we would have exactly the identity matrix. Well, what we can do is we can compare our matrix to this to see if the difference is statistically significant. Because we want our correlation matrix to differ statistically to the identity matrix. And it's really kind of cool because that's exactly what Bartlett's test does for us. Okay? So Bartlett's test, the null hypothesis. Is our correlation matrix is equal to the identity matrix. And the alternative is our correlation matrix is not equal to the identity matrix. Okay? Now, guys, clearly, P's greater than 0.05 are problematic, because what would happen with a p-value greater than 0.05, we would fail to reject the null, which would lead us to believe that there's not enough difference between the identity matrix and our correlation matrix to assume that we don't have too many low correlations. So we kind of hope for statistical significance here when we run this. Okay? Now, let's... Now, the command in R is called core test Bartlett, and we just run this on our data, okay? But to get this option to pop up in R, we have to install what's called psych package. All right, so let's get out of here, go over to R, and let's see if we have too many low correlations. So I need to install packages. Select a crayon. Someday. Okay, this is annoying. Don't you just hate the spinning wheel? I was doing some stuff this morning and I probably should have restarted my computer. Anyway, you finally get that. Choose our buddies from UCLA. Actually, I'd call them my buddies. I've never met those guys. Wow, this is taking forever. All right. So library, psych, and we're set to go. So guys, we're going to run the core test, Bartlett, of our data. You'll see that the underlying probability distribution is a chi-square distribution. We have a chi-square statistic of 180.3, extremely high. We have a p-value that's negative 30, so very, very, very low. And degrees of freedom equal to 15. All right, so what we conclude that here is our p-value is less than 0.01, so low correlations. Are not an issue. All right, gang, what about high correlations? High correlations are much easier to address. Again, Bartlett's correlation, or Bartlett's test examines low correlations only. For high correlations, to see if we have too many of those, All we have to do is take the determinant of our correlation matrix, and is that's not true, 0.00001, 4 zeros. And if the determination, if the determinant of our correlation matrix is greater than 0.00001, then we have no problem with high correlations. Now, guys, again, what's the big issue with high correlations? Well, it's that M word again, multicollinearity. That may be a test question. Spell multicollinearity. Guys, let's jump out, go back to R. Let's run the determinant of our correlation matrix. And we get a value for the determinant of 0.074. So 0.074 is clearly bigger than this. And we have no issue, okay? Now, the next thing I told you that we would examine was what we call normality. And first of all, something I want you to know is normality is not an issue unless you seek to generalize. So if we're just worried about algebra and calculus and just looking at the underlying structure of displacement test, and we're not seeking to generalize to the larger population, then normality is not really an issue. Guys, normality, the easiest way is just eyeball, create some histograms and see if they look like they reasonably came from a normal distribution. If you're doing this as a master's thesis or with the intent to publish, you'd probably want to run a Shapiro-Wilk test. I'm going to just show you one of these. So if I want to look at a histogram, for example, of calculus, then there's a little bit of right tail skewness there, but there's nothing that makes me leery that these scores didn't come from a normal distribution. Look at one more. And statistics, same thing. So the normality issue, I could go through and create histograms for each of the 6 variables. I'm not going to do that because it's something that you guys can clearly do. But, I don't see an issue right now with anything related to normality. Okay? Now, one thing about normality, big old red flag. I'm writing over here and you guys can't even see it, okay? So a big red flag, anytime you have dichotomously coded or Likert data, then clearly the normality assumption is violated for these 2 types of data. So, that's something that that you'd really need to address if you're using factor analysis or principal component analysis if you have that type of data. Guys, I don't know. I think we're ready to get into some cool stuff. One more thing, sample size issue. I think we want 300. I think we need 500. And we'd love to have 1,000. Okay? We have 73. So you do the math. So is there a sample size issue? Yes. But the good news there is once we get into this reduction process, there's a determinate measurement that we can look at that actually tells us whether or not that sample size seems to be problematic with our structures. So.